Hello everyone, and I am Sunanda, and I am truly honored to be presenting this session on behalf of Gudsky Research Foundation, an initiative that making advanced AI learning accessible to everyone. It's completely free of cost for 6 months. Our mission at Gudsky is simple yet powerful to democratize applied AI and ML education and also helping learners, professionals and understand real world AI concepts in a way that practical, engaging, and deeply insightful. In today's session, we'll explore one of the most fascinating and foundational models in machine learning, the decision tree. By the end of this session, you'll not only understand what a decision tree is, but also why machines need to make decisions, how they do it, and where they are used in real life, from credit scoring to medical diagnosis. So, let's see how machines actually think and decide. Okay, then so here is the structure of the decision tree. Like it will have the root node and then decision node, then leaf node. So it is a structure of the decision tree and why machines need decisions. So now think about your day. You make hundreds of small and big decisions. Should I wake up now or snooze my alarm? Should I take the bus or drive? What should I eat for lunch? Humans constantly make decisions, often unconsciously, and that's exactly what we want machines to do. Machines today, like self driving cars, banking systems, and even your Netflix recommendations, must make autonomous decisions based on data. Let's look at a few quick examples like credit approval, medical diagnosis, recommendations, all those things. If we go for credit approval, when you apply for a loan, the bank's system has to decide like we have to approve or reject. It checks for factors like income, credit score, and employment status. And if we go for medical diagnosis, AI tools helps doctors decide whether a patient is at risk for diabetes or heart disease based on the given lab reports. And if we go for recommendation, Netflix, Amazon or YouTube, they all deciding what to suggest to you next based on your viewing or shopping patterns. But here is the interesting part, all these decisions happen under uncertainty. Machines rarely have all the facts. That's where decision tree comes in. Decision trees provide a transparent rule based reasoning system. So it is a rule based reasoning system, a structure that not only make predictions but also explains why it made a certain choice. That's why they are so important. They make AI explainable and trustworthy. So in in our daily life, why we use decision trees? So why do data scientists love decision trees so much? Because here is the secret, they are simple yet powerful. They work just like human logic, a series if or else questions leading to a decision. For example, if it's raining, take an umbrella. If it's sunny, wear sunglasses. That's literally how a decision tree thinks. They are among the most interpretable ML models. Even prediction can be broken down into human readable rules. They handle both categorical data like color equal to blue, green, red, and numerical data like age, salary. So these terms, they even capture non-linear relationships, that meaning they can learn complex patterns that simple models like logistic regression might miss. And the best part is there is no need for data scaling or normalization. You can feed raw data and the tree figures out pattern by itself. Decision trees are not always the most accurate, but they are incredibly flexible, explainable, and widely used, especially in industries where transparency matters. So here is the slide why we need decision trees. And now decision trees in machine learning. Now where do decision trees fit in machine learning? They belong to the category of supervised learning. That means the model learns from the labeled examples. Decision trees can handle two main types of problems: classification, regression. Classification means predicting categories, for example, spam, not spam, disease, healthy. And if we go for regression, predicting continuous values. For instance, predicting house prices or sales amounts. But wait, decision trees don't stop there. They also form the foundation for advanced models like random forest, which use multiple trees together to reduce variance. Variance means like bagging. Gradient boosting, which builds trees sequentially to reduce bias, that means boosting. So even though a single decision tree may not always be the most accurate, it plays a crucial foundational role in more powerful ensemble systems that dominate modern AI today. So, and this session's agenda is, let's quickly look at what we'll cover in today's lecture. So here is our roadmap for this session, understanding like what decision trees are, how they visually represent decisions, and exploring splitting criteria like entropy, information gain, and Gini index, understanding overfitting, and how to fix it using pruning. Looking at strengths and limitations of decision trees in real world practice, seeing applications across healthcare, finance, and manufacturing. Finally, we'll introduce ensemble extensions like random forest and gradient boosting. By the end of this session, you'll not only understand decision trees but also how they connect to more advanced AI models. Okay? And now we'll see the exact. So let's begin. What exactly is a decision tree? Think of it as a flowchart like structure that helps us making predictions by breaking down a decision into smaller steps. It has three main parts. As we at first we saw this like nodes, branches, and leaves. Nodes means where a decision is made, and the branches representing possible outcomes of that decision. Leaves means the final results or predictions. At the top we have the root node, which uses the entire dataset to make the first big decision. So each internal node like splits the data further. For example, if we go, if temperature is greater than 30 degrees Celsius, there we'll have yes or no. Like each branch shows what happens next based on that answers. Finally, each leaf node goes a prediction. For instance, if outlook equal to overcast, play tennis. Yes. So the beauty of this structure is that isn't just a series of logical rules learned from data, exactly how humans reason through problems. As we previously saw this picture, like here is the root node and the decision and the leaf nodes. Okay, and now we'll see the tree structure explained. Here visually a decision tree looks like a branching diagram, like an inverted tree. At the top you start with a question, that's your root node. Okay, and depending on the answers you move through branches, each representing a condition until you reach the leaf where the decision or prediction is made. In real machine learning tools like scikit-learn or visualization platforms, you will see trees drawn with boxes and arrows. They show how the data flows and where it's get divided. For example, in the play tennis dataset, the tree might start with outlook at the root. If outlook equal to overcast, then we play yes. If outlook equal to sunny, we check humidity. If outlook equal to rain, we check wind. And that's how we arrive at our final predictions step by step, visually and logically. Now we'll see classification versus regression trees. Now decision trees come into two flavors like classification trees and regression trees. Classification trees means where the goal is to predict a category like yes or no, pass or fail, fraud or not fraud. If we go for regression trees, where the target is a number like predicting house price or age. In classification, the tree tries to create nodes that are as pure as possible, meaning most data points in a node belongs to the same class. We measure this purity using entropy or Gini index. In regression, we are dealing with continuous values. The tree chooses splits that minimize variance That is, it groups similar values together. So while the structure of both trees is similar, their splitting criteria differ based on whether we are predicting labels or numbers. Okay, and if we go for an example data set like play tennis, so to understand how a decision tree works, let's use simple dataset called play tennis. It has the features like outlook sunny, overcast, rain, and the temperature is hot, mild, cool, and the humidity high, normal, wind weak, strong. And the target variable is where a person decides to play tennis, yes or no. Now, tree analyzes the dataset and finds which feature provides the best split, the one that separates the data into clear, like play equal to yes and play equal to no, two groups. For example, outlook equal to overcast, always play, like yes. Outlook equal to sunny, so based on the sunny we'll take the decision like if we play or not. And if the outlook equal to rain, depends on the wind, we'll play or not. So this is how we'll take a data set and we'll explain the decision tree concept here. This data set is classic because it clearly shows how a tree's logic flows, and also how we learn about entropy and information gain, which we'll get into next. How decision trees grow. So how these trees actually grow. The process is called recursive partitioning, meaning the data keeps getting divided into smaller and smaller subsets based on certain conditions. At each step, the algorithm looks at all the features and chooses the best split, the one that makes the group as pure as possible. It continues splits until one of these happens. Like it will continue the process, like splitting process, and until these reasons might occur, like all samples in a node belong to the same class and no more features are left to split, and there is no chance to split, or stopping conditions like maximum depth. Okay, if the maximum depth is reached, oh, we'll stop the decision tree there. And this is called greedy approach. The tree doesn't look ahead, it just pick the best split at the current step. But there is a catch here. If the tree grows too deep, it can't overfit. It learns the training data perfectly but fails on the new data. So that's why we must always strike a balance, deep enough to capture patterns but not so deep that it memorizes noise. And now we'll see the splitting criteria overview. Alright, now we understand how decision tree grow. Let's move on the heart of how they decide where to split, the splitting criteria. Think of it like this. Every time the tree reaches a decision point, it asks which feature should I split, or next to make the decision data as pure as possible. The goal is to make the data inside each branch homogeneous, or as we say in machine learning, pure. Pure means most of the samples in a node belongs to the same class. For example, if you are predicting whether people will buy a product or not, one node might contain 90% of buyers and 10% non-buyers. They are pretty pure node. Okay, another node might have 50-50, that's impure because it's mixed. So a good split in one that reduces this impurity and makes each branch more certain. And to measure this, we have three main tools. One is entropy, information gain, and Gini index. Entropy means measures randomness or uncertainty. Information gain means measures improvement after a split. Gini index means measures impurity directly. So here we have different algorithms prefer different criteria. ID3 uses entropy and information gain, and C4.5 improves on ID3 using information gain ratio. CART, which means classification and regression trees, used the Gini index. The ultimate goal is to make every split increase purity or decrease disorder. Okay. And now we'll see the entropy. Let's start with entropy, a key concept borrowed from information theory. Entropy means the level of uncertainty or impurity in a dataset which we take. Okay, imagine you are tossing a coin. If the coin always lands on heads, there is no uncertainty, entropy equal to 0. If it's a fair coin, head and tails are equally likely, uncertainty is maximum, so entropy is equal to 1. So entropy tells us how unpredictable the data is. In machine learning, it works the same way. If all the samples in a node belongs to one class, say everyone in that group buys, the node is pure and the entropy equal to 0. If it's half, buy and not buy, entropy equal to 1, maximum uncertainty. So here the intuition, lower entropy equal to more certainty, the better split. Higher entropy equal to more randomness, the poor split. Entropy is mostly used in ID3 and C4.5 algorithms to decide which feature to split on first. So let's explore how we calculate it next. So here is the entropy concept. Like here we'll see in a picture, like high entropy equal to mixed classes. Like if we basically we take this example at coin toss randomness, and low entropy equal to pure node. Pure node means all those are denoting like a same squares with a blue color. So range equal to 0 or 0 to 1, highly mixed. So here intermediate entropy. So these are the divisions, like first one is high entropy with mixed classes, low entropy that is pure only same one class, and intermediate like only a medium type of entropy. So this is the entropy concept. And if we see the formula and explanation, the formula of entropy looks like this: h of s equal to minus summation pi belongs to by pi log 2 of pi. So where pi is the proportion of samples belong to class I. The logarithm base 2 means we are measuring information in bits. Entropy always lies between 0 and 1 for binary classification. 0 means pure, one class only. So as we previously discussed in the diagram, like all the same colors, all the same classes, which means pure, 0 class only. 1 means impure, equal mix of classes. Let's make it practical. Imagine you have a node where 80% of people said yes and 20% said no. This node is quite pure because most people agree entropy is low. Now imagine another node with 50% yes and 50% no. That's highly uncertain. Entropy is how high. So when building a decision tree, the algorithm always tries to minimize entropy at every step to make groups more predictable. Okay, this is how the formula and explanation of entropy, and then we'll see the entropy example explanation. Alright, let's calculate it together. Suppose we have a data set of 14 samples, like 9 labeled equal to yes and 5 labeled no. So here we take P of s equal to 9 by 14 and approximate value will get 0.64. So P of no equal to 5 by 14, approximate value we get 0.36. Now plug these into the formula, like h of s equal to minus 0.64 log base 2, 0.64 plus 0.36 log 2 base log 2 and 0.36. Here h of s, if we calculate, will get the approximate value of 0.94. This tells us how the entropy of the dataset is 0.94 bits, meaning it's quite mixed and impure. The tree will not look for a feature like outlook or humidity that reduces this entropy the most after splitting. That's how it's find the best feature to split on. So now we'll see the information gain. So once we understand entropy, the next question is, how do we know if a split made our data better or not? So that's where information gain comes in. Information gain measures how much uncertainty or impurity has been reduced after splitting the dataset on a feature. In simple words, before the split, the data is messy. After the split, each branch should be purer. The difference in purity equal to information gain. It's like this. So, okay, I'll say a scenario like you had a box full of mixed fruits. Those are messy like apple, oranges, banana, etc. You sort them by type. Now, each box has one fruit type, right? That's high priority. The gain you achieved in organizing is like information gain. So the higher the information gain, the better the feature is for splitting. Algorithms like ID3 and C4.5 rely heavily on this measure. At each step, the feature with the highest information gain becomes the next split point in the tree. Okay, now we'll see the information gain formula and interpretation. The formula for information gain look like this. Information gain like Ig s comma a that equal to h of s minus summation of s of v, s base of v, and s and h of s base v. So here h of s means entropy of the parent node and the h of s base v entropy of each subset after splitting on a feature A. S or S base V proportion of samples in the data set. So essentially you take the weighted average of child entrophies and subtract it from the parent's entropy. If the child nodes are very pure, their entropy is low. So the information gain is high. If the child nodes are still messy, the gain is low. So we want to choose the feature that gives the maximum information gain. That's the most informative feature at the stage. So here is the quick example of information gain. We'll see. Let's bring back our play tennis dataset as we previously discussed. Suppose we decide to split the data on the feature outlook, which can be sunny, overcast, rain. So we'll calculate entropy for each of these subsets separately like we did before. Then we did the weighted average and subtract it from the parent's entropy. So example results are information gain outlook equal to 0.246 and information gain temperature equal to 0.029, information gain humidity equal to 0.151. So which one is the highest here? Outlook with an information gain of 0.246. So the algorithm picks outlook as the root node of the tree. That's the starting point for all the decisions. This process like repeats recursively every time, choosing the best feature for the next split until the data becomes fully separated. Okay, and then we'll have a Gini index concept. So another way of measuring impurity. So this is Gini index. Gini is used in the CART algorithm like classification and regression trees, which is one of the most popular implementation algorithm today. The idea behind Gini is simple. It measures how often a randomly chosen element would be misclassified if we labeled it randomly according to the distribution. Here's the formula like Gini equal to 1 minus pi power 2. Okay, if all samples belong to one class, Gini equal to 0 pure. That all we know. If classes are evenly mixed like Gini equal to 0.5, maximum impurity for binary problems. So okay, let's clear this. Let's take an example. If a node has 80% yes and 20% no. So here is how we will calculate the Gini. 1 minus 0.8 square plus 0.2 square that equal to 1 minus 0.64 plus 0.04. Here we will get the result of 0.32. So this node is fairly pure. Decision trees using CART choose the split that produces the lowest Gini value, meaning the purest children's nodes. Okay, so we'll compare Gini and entropy. Like here now a common question, should you use entropy or Gini? So well, Both are impurity measures and often lead to similar results. The difference is entropy is based on information gain, it gives more theoretical understanding of uncertainty. Gini index is simpler and faster to compute. For a 50-50 binary split, entropy equal to 1.0 and gain equal to 0.5. So both indicate maximum impurity. Okay, here as we previously discussed, like concept is measures information in bits and Gini index measures probability on misclassification. Formula as we previously discussed, and range equal to here entropy 0 to 1 pure impure and Gini index 0 to 0.5. And speed, if we take speed of this, entropy is slow due to log and Gini index is fast and simple. Algorithm here we used in entropy is ID3, C4.5 and Gini index we use CART. Like CART means as we previously discussed, like classification and regression. In practice, many data scientists prefer Gini because it's computationally lighter, especially on large datasets. But both capture the same idea, how mixed or pure dataset is. So next we'll see the stopping splits. Now here is something important, we can't keep splitting forever. So if we let the tree grow endlessly, it will memorize the training data, which means overfitting. So we need to decide when to stop fitting. So there are few common stopping conditions, like there are conditions to stop this, like pure node equal to all samples belong to one class, then we'll stop that condition and no more features. So we'll complete all the cases and no more splits, then we'll stop. Minimum samples per node, for example, stop it if fewer than 5 samples are left. Maximum tree depth, limit how deep the tree can grow. Okay, at that time we'll stop. No information gain, if the next split doesn't improve purity, then stop. So these are all the cases we'll stop splits. Example, if a node already have 95% yes and 5% no, splitting further doesn't make sense. It will just overcomplicate the model. So these conditions make sure your tree remains manageable and it will prevent the overfitting and performs well on new unseen data. So here is how we'll split the decision trees and we'll stop the splitting on these conditions. And now we'll see the overfitting in decision trees, as we previously discussed in many sessions about this overfitting. So in decision trees, now that we know how trees grow, how comes one of the biggest challenges in machine learning is overfitting. So what does overfitting mean? Imagine a student who memorizes every line of their textbook but can't answer a single question that's asked differently in the exam. So this is called overfitting. So similarly, an overfitted decision tree memorizes every small detail of the training data, including the noise, mistakes and outliers. You will notice it perform perfectly on the training dataset, maybe even 100% accuracy. But when you test it on new unseen data, the performance drops drastically. Why? Because the data didn't learn the general rules, it just memorizes the examples. So if we take an example, let's say you are predicting student fail or pass results. An overfitted tree might say if student ID equal to 101 and study 2.7, he will pass. That's not a general rule, it just memorizes one case. Overfitting usually happens when the tree grows too deep, too many branches, too specific. So to prevent that, we need to control complexity, and that's where pruning comes in. So here we'll see the tree complexity and then we'll see the pruning concept. Now we'll see the tree complexity example. Let's visualize concept complexity with a simple example. Suppose we are building a model to predict whether customers buy a product or not. A shallow tree, maybe just 2 or 3 levels, might say if age greater than 30, likely buy. This is simple, interpretable, but may not be perfectly accurate. Now, a deep tree might say if age greater than 30 and income is 50,000 and city equal to Delhi and previous purchase, yes, buy. That's very specific, and while it's fit your past data perfectly, it might fail when a new customer from Bangalore or Chennai comes in. So the deeper the tree, the more it fits in the training data, but the less it can generalize. We call this the bias variance trade-off. Shallow trees have high bias, but it's too simple, and deep trees have high variance and it's too complex. The goal is to find the sweet spot where tree that's just deep enough to learn patterns but not so deep that it memorizes noise. So to fix overfitting, we use a process called pruning. So this is the pruning in decision trees, which literally means cutting back the tree. Think of a pruning a real tree like in your garden. So when you remove weak branches, the tree becomes stronger and healthier. Same logic applies here. So pruning removes all branches that don't improve accuracy or that only represent noise in the data. So there are two types: pre-pruning like early stopping and post-pruning, reducing errors pruning. So early stopping means stop growing the tree beyond a certain limit. So it is called early stopping, pre-pruning. And the post-pruning is grow the full tree first and then cut the necessary parts afterward. So the benefits of this is simplifies the decision rules, reduces the overfitting and improves the test accuracy and make the model easier to interpret. Example, if a branch only affects one or two data points out of thousands, it probably isn't worth keeping. Pruning removes it, keeping your model clean and efficient. So this is the pruning in decision trees. As we generally see the pruning in real life as we previously discussed, and we'll go for pre-pruning. So let's understand pre-pruning in detail. This approach stops the tree from growing too big while it's being built. So we set constraints like maximum depth, minimum sample split, minimum sample sleeve. So maximum depth means how many levels deep the tree can grow. Minimum sample split means minimum samples needed to split a node, and minimum sample leaf means minimum samples required to form a leaf. So these parameters prevent the model from creating the unnecessary tiny branches. Like example, if you set maximum depth equal to 5, your tree will stop after 5 levels, even if it could split further. So however, this is what the pre-pruning has a catch. If you stop it too early, the model may underfit. That means it doesn't learn enough patterns. Imagine cutting a plant before it even grows, you miss out the flowers. So it's all about balance, not too shallow, not too deep. So if we go for next slide, that is post pruning. Now, next we have post pruning, also called reduced error pruning. Here we first let the tree grow fully, capturing every pattern it can. Then we first let the tree evaluate it on a separate validation dataset. We check each branch or subtree. Okay, if removing it doesn't reduce accuracy, we cut it. If it removes if it improves accuracy, we definitely cut it. Okay, so this is what the post running. This process continue until we reach the simplest version of the tree that performs well on unseen data. Example, if removing a small branch improves the test accuracy by 2 to 3%, we keep it pruned. Okay, it's like cleaning your code, removing redundant lines to make it faster and easier to understand without changing what it does. Okay, so if we see an example of pruning, let's take a practical example from our play tennis dataset. Before pruning, you might have a complex rule like if outlook equal to sunny and humidity equal to 80%, and wind equal to weak, that means play, yes. After pruning you might simplify it to if outlook equal to sunny and humidity equal to high, play no, otherwise yes. Okay, notice how much cleaner it is. Fewer conditions but the same logic. That's the essence of pruning. You keep only the important general decision rules and remove the overfitted ones. Visually, you can imagine the tree changing from bushy and tangled to slim and clean. The outcome is slightly lower training accuracy, much higher test accuracy, meaning your model works better in the real world. So, this is what we'll see. We saw the pruning example. Now, we'll see the bias variance trade-off. Let's talk about one of the most fundamental principles in all of machine learning, the bias variance trade-off. Bias is the errors from making assumptions, usually by using a model that's too simple. Variance is the error from being too sensitive to training data. The model is too complex. Here is the relationship. High bias means underfitting, high variance means overfitting. High bias means the model is too simple, it misses the patterns like missing values. High variance means overfitting, the model is too complex, it memorizes the noise. Okay, decision trees that are shallow have high bias. Trees that are deep have high variance. We aim for a balance. That's a tree just right. Imagine a curve shaped like the letter U. On the left, error is high due to bias. On the right, it's high due to variance. That sweet spot in the middle where the tree performs best. Good accuracy on the training and testing data. This is why we tune high parameters like maximum depth or min sample sleeve to find the perfect balance. Okay, we'll see now high parameters for control. Now that we talked about bias and variance, let's explore about actual high parameters that give us control over tree growth. So here are the main ones: maximum depth, minimum sample split, minimum sample leaf, and maximum features. So here maximum depth means it limits like how deep the tree can grow. So limitation of a tree like how much it have to grow. And minimum sample split means so it has the minimum, only minimum samples need to split, and the more than that we don't want to split, like there is a stoppage from there. And minimum sample leaf means samples in the leaf node. Maximum features means how many features to consider at each split, especially used in random forest. So by tweaking these values we can control the complexity of tree and avoid overfitting. So if we take an example for a medium sized dataset, like setting maximum depth equal to 5 and minimum sample leaf equal to 10 often gives a good balance between accuracy and interpretability. In professional practice we use grid search or random search to find the best combination of these parameters automatically. So if we see advantages of decision trees here, let's take a step back and appreciate why decision trees are so widely loved in machine learning. Here are some major advantages. These are easy to interpret. Like you can literally read the decision path and handles both categorical and numerical data. So it's very easy, right? No need for data normalization or scaling. Can handle missing values using surrogate splits. By using the splits we can handle the missing values, like fast to train and make predictions. Like if we fastly train the model, then it will make a good predictions, and mostly they are explainable. Like if we see a decision tree we can explain, like if we see the lines of code many of them will not explain. Like so for instance a doctor can understand and trust a rule like if blood sugar is greater than 140 and age is 50, it may be high risk. It's transparent and human readable, something neural networks or deep models struggle with. Okay, That's why decision trees are used across healthcare, banking, education, and manufacturing. Everywhere, clarity and trust are essential. So these are the decisions of decision trees and the limitations of decision tree. Now let's be honest, no model is perfect and decision trees also have limitations. Here are some key ones. They can overfit if not pruned properly. So okay, if if we take a tree an example, the tree will grow in depth. We can't prune it. This may be overfit. So the and this is the reason, and they are unstable. Even small data changes, they can change the entire tree structure. If one thing in the data set may change, we have to change the entire tree structure. Okay, this is the limitation. And the lower accuracy compared to the ensemble models like random forest or XGBoost, it having low accuracy. Okay, poor handling of continuous outputs. Like if we take a step like predictions instead of smooth curves, so this may be the poor handling. And biased toward dominant classes. So if we have the dominant classes in the data set, so it may be biased if the data is imbalanced. Okay, example, if your data set has 90% no and only 10% yes, the tree might keep predicting no just because the majority. So this is how the decision tree will fail. So these are the decisions limitations of decision trees. So while decision trees are great for learning and interpreting, we often combine them into assembles to improve accuracy and stability, something we'll explore in the next part. Like scalability concerns. So now that we have mastered the theory, let's look at what happens when you use decision trees in the real world, especially when our datasets get really big. So scalability is one of the main concerns with traditional datasets. Traditional trees, traditional data trees. Here is why. Each time the algorithm builds a split, it has to. So if a algorithm build a split, it has to check every feature at every possible threshold and compute impurity like Gini or entropy. All these candidate splits. That's a lot of calculations, right? Let's say an e-commerce company has 1 million customers and 200 features, things like income, location, browsing time, all these things. For each level of the tree, the algorithm has to test millions of potential split points. That's why building deep decision trees on huge datasets can take a lot of time and memory. So real world example in banking, a credit risking model might take hours or even days to train if you use a single big tree. That's where distributed versions, ensembles or approximations like random forest can be rescued. They handle data in parallel to keep training practical. So remember, decision trees are powerful, but very large or high dimensional data, they can become computationally expensive. So if we see the interpretability versus accuracy, one of the biggest trade-offs in AI is interpretability versus accuracy, and decision trees are the perfect example. Decision trees are loved by being interpretable. You can literally trace the decision path step by step. For example, a simple rule like if attendance is greater than 75, predict pass is easy for teachers or policymakers to understand, right? It's very simple criteria. If student having that much attendance, that means pass, so no need to marks all those things. But as trees get deeper or when we combine hundreds of them into ensembles, they become less interpretable through more accurate. So let's compare. A simple tree equal to easier to explain but maybe 80% accuracy. A larger ensemble like XGBoost hard to interpret but 95% accuracy. So we have to decide like if the uh, like what matters more for your case. If transparency is crucial, like in medicine or law, use simpler trees. If performance is critical, like in stock prediction or ads, use NSMLs. It's like simplicity versus perfection. You rarely get both. Okay? A large tree or ensemble might include 20 conditions and deliver 95% accuracy, but it's unreadable to humans. Okay? This is what the interpretability versus accuracy. And now we'll see the example where trees shine. Now let's look at a situation where trees absolutely shine. They perform best when, at which time, the dataset is small to medium sized and the features are clearly defined like yes, no, numeric thresholds, and the problem needs transparent reasoning. Okay, so if we take the examples here, healthcare, if fever equal to yes and cough yes, diagnosis equal to flu. So doctors love this kind of clarity, they can validate each step. In agriculture, if soil moisture is less than 20%, irrigate crop. Great for IoT based smart farming systems. So, in education, if attendance percentage less than 50 and assignments less less than 2, at risk of failure, right? If attendance is low and assignment submission also low, it may be the failure. So these are straightforward rule based systems where explainability and quick computation more than tiny boost in accuracy. So if we take an example where trees fail. So but trees aren't superheroes from every scenario. So they are struggling with high dimensional data like images or audio, like and continuous targets that need smooth predictions, like regression task with smooth patterns. Like in regression we'll having the continuous outputs and the high noise, which means more errors, measure random fluctuations, like interpretations, like overlapping classes means fuzzy boundaries. Example, if we take here image classification, decision trees can't capture relationship between pixels, right? So deep learning models like CNN are far superior here. So if we take image classification, we use the CNN model here. If we go for stock prediction, stock price fluctuate continuously. Like stock prices are not same every time. It will change continuously. So decision trees create step like jumps instead of smooth curves, leading to poor forecast. Okay, noisy or changing data. So okay, if a customer behavior changes daily, a tree keeps splitting endlessly, trying to memorize noise instead of patterns. So while trees are great for structured tabular data, they are not ideal for high complexity or high dynamic problems. So if we take an example of medical diagnosis here, one of the most impactful applications for decision tree is medical diagnosis systems. Why? Because they mimic how doctors think. Let's imagine a simplified decision tree here. So fever is root node here, yes, and the cough, yes, it means flu. So fever, yes, cough, no. So it means typhoid, fever, no, it means healthy. So that's literally how doctors make decisions, a series of logical if then, as we used in real world scenarios. So benefits of this is, if the transparency, that means doctor really can see why the model made that diagnosis, and speed, quick initial assessments, like it have the more speed and the safety, easy to verify or override if it's wrong. So we can easily verify, right? We'll check easily, like in decision tree. Real world use case, we'll see predicting diabetes risk and heart disease probability or COVID-19 severity from patient data. So, okay, in rural hospital with limited specialist, tree based AI tools can act as virtual medical assistants, right? So, and now we'll see the credit scoring and fraud detection. One more example in finance, decision trees are everywhere from loan approvals to fraud detection. So, here we take a case if credit score is less than 600 and income is less than 30,000, reject the loan. If credit score is 700 and no defaults, approve loan. Okay, each rule is transparent here, so banks can explain decisions to regulators why this loan was rejected. In fraud detection, trees help identify suspicious patterns like unusual high value purchases, transaction in odd locations, or spending at 3 a.m. in another country. Each of these rules become a branch that flags possible fraud. So when you swipe your card behind the scenes, dozens of tree-based models are deciding in milliseconds whether the transaction looks normal or not. So, and also customer segmentation. Business thrive on understanding their customers, and decision trees make make this role very simple. So suppose if we take a retail store which wants to identify customers by spending behavior, if age less than 25 and spending score greater than 70, young high spenders if age greater than 50 and income less than 30k. So in these cases, so if age greater than 50 and income less than 30, budget shoppers. So if so okay, I'll explain once again. If age is less than 25 and spending score is greater than 70, young high spenders, will classify them as young people high, so the people who spend much. If age is greater than 50 and income is less than 30k, budget shoppers. If age is 20 to 40 and income is greater than 60k, working professionals. Each rule defines a segment here. So use cases are marketing means we'll have the personalized discounts like 50-50 off, 20% off, like one by one, like buy one get one. Retention means identifying loyal versus at risk customers. So we'll identify the who is the loyal customers and who will the risk customers, like upselling, offering premium products to high spending segments. So e-commerce gains like Amazon and Flipkart use these principles often as part of bigger assemble systems to recommend what you will want next. So manufacturing quality control in, and also decision trees also play a big major role in manufacturing and industrial automation. Here is the idea. During the production, machines collect tons of data: temperature, pressure, vibration, material type, conveyor speed, etc. A decision tree learns from this historical data to predict will the product be defective or non-defective. It acts like virtual quality inspector, like checking the process parameters, deciding whether the current items meet standards. So if we take example here, if pressure is greater than 250 psi and vibration is greater than 7 Hz, high defect risk. Such system allow factories to defect issues early, reduce waste and maintain consistent quality. So from car manufacturing to semiconductors, tree based models are quietly ensuring the product we used are safe and reliable. So if we go for other application, decision trees are everywhere. You need rule based reasoning. Some interesting areas are sports analytics, recommendation systems, agriculture, education, and IoT edge devices. Like Sports analytics means predicting match outcomes like he will hit a six or not, he'll out or not. So these are the sport analytics and recommendation system. If user liked X, recommend Y. So if user like the uh, horror movies, then recommend the same feed like horror movies. In agriculture, detecting plant diseases based on temperature and humidity, and education predicting student grades or dropout risk, and IoT edge devices like making quick autonomous decisions without cloud support. So these are the applications. Why they are so popular means because they offer clarity, speed and transparency, perfect for environments where decisions must be fast and explainable. So we discussed all the decision trees part there. Now we'll see the ensemble. Now we are about to take things to the next level. A single decision tree is powerful but often a weak learner. It might perform well on some data and poorly on others. To overcome this, we combine multiple trees, a concept called ensemble learning. So, an ensemble method merges prediction from several trees to create a stronger, more reliable model. So, there are two main types: bagging, like bootstrap aggregation. So, it means it reduces the variance, that means errors, by training many trees in parallelly. So, not only one tree, ran by parallelly run many trees and many samples, like example random forest. Boosting means reduces bias. Bias means missing values by building trees sequentially, each correcting the mistakes of the previous one. So here we use the gradient boosting or XGBoost. So this is where machine learning becomes truly industrial grade. Ensemble takes the interpretability of trees and multiplies their accuracy and robustness. Okay, now we'll see the random forest. Now that we have built strong individual trees, it's time to grow a forest, a random forest. A random forest is an ensemble of many decision trees that work together to give more accurate, stable and reliable results. So here how it works: each tree is trained on a random subset of the data and also a random subset of features. This randomness ensures that no tree are identical. So where it's time to make a prediction in random forest means, for classification every tree votes for a single class and the majority wins. For regression we take the average of all tree predictions. The simple trick massively reduces overfitting because even if one tree is wrong, the others balance it out. Advantages of random forest is works well for both classification and regression. Handle large, noisy and incomplete datasets. It's naturally resistant to overfitting and offers feature importance insights telling us which inputs matter most. So if we take an example here, in banking random forest are used for credit scoring, fraud detection because they provide both accuracy and explainability. The only drawback is interpretability, because since it combines hundreds of trees, it's harder to explain every single decision. But that's a small price to pay for its incredible performance. So in short, decision tree equal to one mind, random forest equal to a team of minds working together. Like if we go for gradient boost, so here is the random forest, like connecting all the decisions. Okay, and we see the gradient boosting. Now let's take things up a notch with gradient boosting, another assemble technique that's a bit more sophisticated. While random forest builds trees independently, gradient boosting builds them sequentially one after another. Each new tree learns from the errors of the previous ones. Here is the intuition. Imagine like you are tutoring a student. You first test them, then see where they went wrong, and next time you focus only on those weak areas. That's exactly where gradient boosting does. It starts with a simple model like small tree that makes some predictions, then it calculates the residuals, the difference between predicted and actual values. The next tree is trained specifically to fix those errors. This process repeats many times with each tree improving the model step by step. So mathematically, gradient boosting uses gradient descent to minimize the overall loss function. The final model combines all three outputs, producing a strong, accurate predictor. Popular implementations include XGBoost, like extreme gradient boosting, light GBM, light gradient boosting machine, cat boost for categorical data. So these are the superstars of machine learning competitions today, combining tree interpretability with near deep learning level accuracy. Okay, here are the gradient boosting. We see the first initial tree like f naught, and then by from that we see the h1 and that too. So here first f naught, and from f1 that equal to f naught plus h2, and f2 equal to updated model like f1 plus h2, and the final strong model. So like sequentially it builds the trees. And decision trees in ML pipeline. Let's now see how decision trees fit into a machine learning pipeline. From data exploration to production, here is the role they play. Baseline models means before trying to complex algorithms, we often we'll start with a single decision tree to get a quick sense of data behavior and feature importance. Trees help identity which features actually matter for prediction. For example, income might be more important than the zip code, right? Building blocks. They form the foundation for advanced ensemble methods like random forest and gradient boosting, as we previously discussed, and the interpretation tools like black box, white box, all these. They help explain the logic behind the black box model, showing how data features interact. Hybrid systems means sometimes we even combine trees with neural networks for extra performance. So even though decision trees are simple, they are essential part of every data scientist took it from exploratory analysis. So before we wrap up, let's take a moment to appreciate what Gudsky Research Foundation is doing. Gudsky is dedicated to spreading AI and ML education free of cost, empowering learners from all backgrounds to understand and apply artificial intelligence in practical ways. Every video, every concept from data to deployment is crafted to help you think, build, and innovate using AI tools responsibly and effectively. So, if you followed along so far, you are not just learning, you are becoming part of next generation of AI innovators. So, and with that, we come to the end of today's deep dive, decision trees, how machines make decisions. And let's quickly recap the journey we took today. We began by understanding why machines need to make decisions. We explored how decision trees work from entropy to pruning. We saw real world applications, and finally we stepped into real world ensembles. So remember, every AI system you see today, from predictive analytics to recommendation engines, stands on the shoulders of these simple elegant trees. So keep exploring, keep building, and keep learning. Thank you. Thank you for joining the session, and stay tuned. My teammate will continue in the next video, diving deeper into ensemble learning and advanced AI topics. Until then, keep your curiosity growing, just like these trees growing of knowledge. Thank you.